Hello, everyone, and welcome to week 21 of Qubit by Qubit's Intro to Quantum Computing. This week is all about Grover's algorithm. So what is it now? Week number three, four, three, I think, of doing interesting new quantum algorithms. And I think this week we've gotten to one that is often cited as something that is truly exciting for potential quantum applications in the future. Grover's algorithm is pretty difficult to implement, generally speaking, for real physical quantum computers. But it's one of those algorithms where if we could build a quantum computer that was large enough to do this algorithm, it would have pretty significant repercussions on a whole variety of industries. So this is, in my view, one of the most important quantum algorithms just because it has such potential to shake up so many different industries. So with that, let's go ahead and get started. Quick program for today. We'll start off with one quick announcement. As you might be aware, spring break is coming up. I will mention how that's going to work for Qubit by Qubit in just a moment. We'll do our Canvas attendance quiz. Questions from last week, we did have a couple related to, I think around oracles. And so we'll be talking a little bit more about oracles there. We'll do our pre-lab Zoom feedback, lab content, and post-lab Zoom feedback as usual. As I mentioned, a few quick announcements. First one is that this week's homework assignment is a little bit different. It's not your traditional doing problems that are related to course content so much. It's simply to submit your name, how you'd like it printed on your certificate for passing this course. So should be pretty simple this week. We do have spring break coming up, so we didn't want to give you too much stuff to think about. This is just so that we can print and create these certificates in whatever way you would like. There's no other homework, as I said, because it is spring break. And what that means for Qubit by Qubit is that the next 2 weeks of lectures and labs are canceled. There's no lectures or labs going on for the next 2 weeks. So in other words, this Tuesday, we have a lab. The following 2 Tuesdays, we will not. And then things will start up again with a lecture the Sunday following that second Tuesday where we had a break. I think the details of these dates should have been sent out to you, but that is the plan for the next 2 weeks. I will mention as well that we are, well, I guess we already have, according to this, released cheat sheets and the review notebook on Canvas, or I guess will be uploaded on Canvas. I'm not quite sure if it's there yet. But yeah, definitely feel free to check that out, especially if you felt a little bit lost or are struggling a little bit with more recent content. Hopefully spring break gives you a chance not only to relax, but also maybe catch up and review some things that were less clear the first time around. Let me also open up the chat. If you have any questions about this, feel free to throw it in the chat and I'll do my best to answer. Otherwise, let's go on to the Canvas attendance quiz. Lab number today, as always, is 1. The quiz password is 2607. The question for today is which topics from this semester would be the most helpful to review? So I don't think there's any final plans on this, but we are sort of thinking about doing maybe a week of a review lab, or maybe doing some optional lecture lab content sometime toward the end of the course that covers basically reviews some of the content from the course. We're just curious what you think would be the most helpful. This can either be a topic that you are, very interested in and would like to hear more about, or it can be something where you didn't understand the content that we taught as well as you did for some other weeks. So as always, quiz is not graded, but it does count for your lab attendance. So please make sure you do go ahead and fill this out. Okay, pre-lab Zoom feedback. I will put up a poll on your screen right now. So please let me know how you found this week's content on a scale of 1 to 5. So the main thing this week was Grover's search algorithm, as you might guess. That's what we're covering in the lab today as well. Yeah, so let me know, how did you find Grover search? Was it relatively straightforward? Was it a little bit more difficult? So it looks like people are pretty evenly split between a 3 and a 4 out of 5, which is honestly pretty good. I think Grover search is starting to get into the more complicated algorithms. So if you can understand the ideas behind this, then you're probably in pretty good shape. Okay. In the meantime, oh, cool. So somebody just says in the chat, I was just going to say, if you have any topics you want me to talk about, please throw them in the chat. It would be really interesting if you could talk about quantum compilers. I think you mentioned earlier that you were working on one. Yes, yeah, absolutely. So that is unrelated to Grover Search, of course, but I can definitely carve out some time, perhaps in the optional content today, to talk a little bit about quantum compilers. Same question. This is off topic. Where can I find information about the compiler language for quantum computing? If I recall, it's part of my research. Yeah. So I guess to answer that question more quickly right now, there is not a standard language that you either compile to or compile from in quantum computing. So we've, of course, been learning Qiskit in this course. As we mentioned when we introduced Qiskit, there are a number of other frameworks out there that let you write code for quantum computers. And so that's sort of like, that's the, I guess I'll call it the software engineer or like the quantum computer scientist level of programming. What the compiler level is basically going to hardware code. So like code that defines maybe laser pulses or particular optical instruments to use in some kind of quantum, like a photonic quantum computer. That type of language, again, there's many possibilities, right? So somebody mentioned in the chat, OpenQASM is one. There are a number of other proposals out there. And so in theory, you could do a compiler from sort of any of these high level languages to one of the hardware languages. And there's a bunch of different such compilers you could come up with, and each of them, I'm sure, has their own interesting challenges and things associated with them. So the short answer is there's no real standards. Well, there are many possible standards, but there's no single agreed upon standard within the quantum compiler world just yet. I hope that helps. All right. Okay, I think I'm going to hold off on questions here and hop into the question from last week, because that is about oracles, as somebody just said in the chat. And I'll also share the results from our pre-lab poll. Okay. So oracles, of course, important for the Deutsch-Jozsa algorithm, as we saw last week, also important for Grover search. So we are going to have another oracle introduced this week for Grover search. So it is important to understand the role of an oracle. Now, the question here is a pretty general one. What is the role of an oracle? The way that I like to think of an oracle, and I think I might not have done as good of a job last week explaining this in succinct terms, but I think the way that I think about it is it's a function, right? Oracle is really sort of a fancy word for just a function. Now, you might not think that that really changes that much, right? But I think that it can help clarify, kind of like when we learn about linear combinations in linear algebra, that is really just a fancy word for adding things together, right? Whenever you hear someone use the word oracle, it's kind of just a fancy word for a function that does a particular thing, right? So in Deutsch-Jozsa, this oracle or function, as I said, implements a constant or balanced truth table, like we saw last week. For Grover search, it's going to essentially mark the element that we're searching for. We'll talk about this in a second, using a -1 sign instead of +1. So at the core of it, that's all an oracle is. It's a function that does something, which is pretty much the most general definition of a function you can come up with. But an oracle is a specific type of function. There's a few other characteristics, I guess, that are usually associated with them. The first one is that we're usually not allowed to peek inside the oracle to find out what the function actually is. So for example, if I have a function like f of x equals x squared, that's a perfectly usual function. And when I'm looking at the function definition, that's what we mean by looking inside of it. We can see what exactly the function is doing, and so we can predict what it would do to any possible input, or perhaps even a whole series of inputs, right? With this function, I could draw you a graph. Oops. With this function, I could draw you a graph of what this looks like. It's a parabola, without actually computing every single value at x equals 0.1, 0.2, etc. Because I can look at this and do some analysis in my head and figure out some more general properties of it. With oracles, you're not allowed to do this. You just have some function. You're not allowed to peek inside of it. And the only way you can learn things about it is by actually plugging in inputs, right? And maybe after you plug in a few inputs, you start to get an idea of what the oracle is, but you can never be sure unless you actually plugged in every single input and found every single output. So that's kind of what the third bullet point here is saying. We can only ask the oracle questions in the form of sending it inputs and analyzing the outputs. So we can't really, like it says above in the slide, you can't look inside of it and look at any further structure. It's just a box where you put stuff in and it spits stuff out. Now, usually where oracles are used and talked about is when we talk about computational complexity, because the complexity of an algorithm is often talked about as the number of queries or the number of times we have to evaluate the oracle. So in Deutsch-Josa, we had an oracle that was that UF block. And so the complexity of the Deutsch-Josa algorithm we saw was always big O of 1, because you always just needed one UF block, right? In Grover search, we will see that the complexity is unfortunately not order 1. That would be incredible. It does grow with the number of inputs, just not as badly as it does in the classical case. And so we'll see that, well, we won't see it explicitly here, but I'll just mention that if you want to do Grover search on larger and larger problems, you would need more and more of these oracles. Okay, so I guess I'll pause there. Any sort of more general questions on oracles particularly? So somebody says, with the Deutsch-Josa oracle you mentioned last week, that one of the oracle functions was not reversible. Is it this? So let me just clarify what I was talking about with reversibility last week. With the Deutsch-Josa function, that f of x that could be constant or balanced, some of those functions were irreversible, right? In particular, the ones that are constant, because if you have, say, f of x equals 0, you can't know whether x was 0 or 1, so it's irreversible. The oracle that you build out of this, though, is always reversible, right? One of the key points we talked about last week is that when you sort of translate from a classical function to a quantum function, which we call an oracle, it has to be reversible, because everything in quantum computing must be reversible. So in summary, the classical functions, some of them are irreversible. When we translate them to the quantum world, we came up with a version that was always reversible, even when the classical function was not. So designing our own oracle, we're actually going to talk about that a little bit in the optional content this week. So I'll hold off on that question. And the question about implementing an oracle in Grovers. I guess we'll have a simple example of that, because we are going to code the whole circuit today in the Qiskit, in a Jupyter notebook. But yeah, the more general question of how you would design a Grover search oracle for a real world problem, we can touch on toward the end of the optional content. Yeah, okay, so I am going to hold off on these questions about defining more general oracles. Somebody asks, why does an oracle have only 2 outputs, like in Deutsch-Josa, constant or balanced, and -1 or +1 in Grovers? Yeah, good question. I think generally speaking, oracles don't need to have just one output, like one bit of output. I guess a lot of the ones that we've learned happen to. I'm just trying to think off the top of my head if there are other examples that use sort of multi-bit oracles. I'm not sure. I can't think of any, but there's nothing stopping you. You could absolutely have an oracle that gives more than a 1-bit answer. There's nothing wrong with that. Okay, so I think I'm going to hold off on questions here and keep going for the time being, but feel free to hold on to those questions, and I will, of course, as I always do, take more in the optional content. Okay, so quick overview of what we'll be talking about today. Obviously, most of this is going to be on Grover's algorithm. So you can see there the rough breakdown. Toward the end, we are going to hop over to the IBM Quantum Experience and actually code this for 2 qubits. So kind of like in the Deutsch-Josa world, we learned that that algorithm could be extended to more than 2 bits, or more than 1 bit, I guess, in that case. Here, we're going to do things initially with 2 bits, but you can, of course, extend this algorithm to more. The optional content is going to be a few more words on oracles, where we talk about how you come up with oracles and how you might implement them in a real world setting. Okay, so let's start things off with an introduction to Grover's algorithm. Last week, we talked about algorithms, and we said that algorithms usually start off with a problem, they have a series of steps, and they spit out a solution somehow as a result of those steps. So following that same kind of formula, when we talk about Grover's algorithm, we're going to start off with a description of what problem it's trying to solve. So the problem it's trying to solve is what we call an unstructured search. So this is simply referring to searching for an element in an unstructured list. This is actually the exact same problem that we saw last week when we looked at linear search, right? So if you had a database of ages, right, students and their ages, those ages aren't sorted in any way, and you want to find out, are there students that are 19 years old? Then you would use what's called an unstructured search. And that's what Grover's search is. This is in contrast to a structured search, just to sort of provide some motivation for this terminology. A structured search is how you go about finding elements in a list if you already know something about the list. So the easiest example of this is if the list of ages was sorted, right? So I'll just do a quick example. If list was sorted. Because if your list is sorted, there are more efficient techniques for trying to find a particular element, right? Because if I drop into the middle of my list and I see someone who's age 25, I know that if there's someone age 19, they would only exist in the left half of that array, right? I don't need to search any of the elements above that 25-year-old I found because I know that they're sorted. And so that kind of problem has a different solution than an unstructured search. So that's database search, the first point here. Optimization problems can generally be phrased as search problems. So what's a good example here? I guess for this one, a common example is something called the traveling salesman problem. So if you have a number of cities you need to visit, and they're all some distance apart, what is the most efficient way to visit all the cities while traveling the least distance, right? So simple problem to state, turns out to be very hard to solve. But you can phrase this as a search problem by basically saying, okay, there are a whole bunch of different paths I could follow. If there's one path, I could also follow maybe this path. All of these paths allow me to visit all of the cities, but some are going to be longer than others. We don't necessarily have an ordering though, right? There's no way of knowing just by looking at the path, which is going to be longer or shorter. We have to actually write it out and evaluate the whole length. And so this is unstructured search. You have a number of different paths you can go through, and some of them will be longer than others. And you basically want to find if there is a path, of a certain length or shorter, for example. So that's how you can do optimization problems with Grover search. The final point here, I'm not going to talk about in too much detail, but there is a class of problems that we generally call counting problems, right? So for example, finding the mean or the median, the mode, finding the number of times that an element occurs in the list. Basically, yeah, things to do with counting up lists of items. Those can also be done with Grover search, although the extension for how that's done is a little bit more complicated, so I won't get into it now. Okay, so this is the problem that Grover search does. We will talk about the algorithm, the steps of the algorithm on the next slide, but just to get you a little bit excited, the main reason we care about Grover search is because of the difference in time complexity it offers. So the sort of headline moment is right here. The complexity of Grover search is order, or big O, root n, which is a quadratic speedup over classical linear search, which is order n. So last week we looked at this and we figured out why, in the worst case, searching through a list would take n comparisons, where n was the number of items in the list. Grover search can do this in square root of n comparisons, or the equivalent of comparisons, which is significantly faster. Just to give you some idea of how much faster this is, I'll throw up a quick Zoom poll for you to answer this question. Suppose we have a database of 10,000 entries, and we want to find a particular element in that database. How long would this take using both linear search and Grover search? So there's two separate questions in this poll. go ahead and throw in your answer to both of these. Once about half of you have answered, then I will go ahead and do this myself. Yeah, so somebody just asked in the chat here, what is a database search? As another student answered, which is exactly correct, it's like searching through a phone book, right? Or searching through a list of ages. It just means you have some big list and you want to find a particular item in that list. Okay, so about half of you have answered. I will go ahead and do this solution myself then. Now, as usual with these sort of big O notation questions, we have to define what n is. So here we have 10,000 entries, so n is going to be equal to 10,000, which I will also write just for the ease of notation, I guess, as 10 to the 4. Okay, linear search, we know is big O of n. And so that is just going to be 10,000 itself, just n. Right, so no tricks here. Order of n, you don't have to do anything else to the number. You can just say that's roughly how many comparisons it's going to take for linear search. Again, this is in the worst case, right? Okay, then let's look at Grover. Same deal, we have a big O notation, but this time we have root n. And so we're going to be looking at the square root of 10,000. The square root of 10,000, which is just 10 to the 4, is 10 to the 2, which is 100. So the correct answers here should have been 10,000 in the case of linear search, 100 in the case of Grover search, and I just got that by plugging n into these big O notation functions. Now, this is a pretty significant speed up, right? You can look at it sort of more mathematically, or you can just think about it. If you had to do something 10,000 times versus doing something over only 100 times, that's a difference of over 9,000 times that you had to do it, right? And so oftentimes this difference is going to be the difference between feasible and completely impossible, right? Maybe it's possible to do 10 million searches on a particular database, but it would be absolutely insane to try and do whatever 10 million squared is, some massive number with linear search. Okay, so I will end the poll and share results just for interest's sake. Okay, that is kind of our introduction to Grover's algorithm. As I said, the only part left is to talk about the steps of this algorithm. So very similar to Deutsch-Josa, Grover's algorithm uses both superposition and interference to speed up search. So there are only 3 steps to this. It's actually fairly straightforward, although I will say step number 2 is quite complicated. So step 1 is okay. Step 1 is to apply Hadamard gates to all qubits. So I guess in theory, there's a step 0, which is initialize all qubits to ket 0, right? So everything starts off in the 0 state. Then we're going to apply H gates to all of the qubits. And so what that does is it creates a even superposition, like a uniform superposition over all possible states. So in the 2-qubit case, we would start off with 0, 0. And when we apply Hadamard gates to that, we would end up with 1 over 2, 0, 0, plus 0, 1, oops, plus 1, 0, plus 1, 1. Just like that. So when you apply Hadamard gates, this works as well if you go to more qubits. It has the effect of creating a superposition over all possible states. Okay, then step number 2 is the complicated one, like I said, and hopefully this is the one we can spend the most time talking about. It has, I guess, 2 substeps. First, you apply the oracle to all qubits. So we'll talk about what the oracle is in Grover search. And then we apply something called the diffusion operator. So the diffusion operator, we are going to spend a lot of time talking about because it is kind of the most complicated part of this algorithm. It's the thing that makes it work, but it's also not entirely clear why. So we'll get into that. But the short answer of what it does is it induces interference. So it makes the states we are not looking for interfere destructively with each other, and it makes the state we are looking for interfere constructively with itself. And so over time, the state that we're looking for is going to have a higher and higher probability of being observed. And then eventually we're going to observe it and hopefully get the right answer. And then step number 3 is also pretty simple. We measure all the qubits, and it's going to tell us where our expected element is in the list. Now, at a high level, with both Deutsch-Jozsa and Grover search, this interaction between superposition and interference can roughly be thought of, as, going into superposition means you create this uniform superposition over all possible inputs. Then you're going to apply the oracle to that superposition. And so you can kind of think of it as, trying the oracle on every single possible state. But because it's a quantum superposition, that operation only has to happen once, right? Instead of having to apply the oracle to 0, 0, 0, 1, 1, 0, 1, 1 separately, we can apply it to a superposition of all those states in only one step. And that's where a lot of the speed up happens. Then, in order to measure effectively, you need to have interference, right? Because you can do this operation on all the different states, but now you have to be able to measure the one that you want. And oftentimes, in order to do that, you need to interfere. So I don't know if this is helpful, but like the high level goal or the high level description, I guess, of how these algorithms work that use superposition and interference is that you go into superposition to evaluate all the states at once. And then in order to measure, you need to cause the states you don't care about to go down, the states you do care about to go up. And so you measure the correct answer. And that's what interference does. Okay, this is it for the Grover search algorithm, by the way. There's only these 3 steps, but like I said, step 2 can get a little bit complicated. So let's talk about them in a little bit more detail. As is often the case, we're going to have a fun analogy to go through this algorithm. We're going to try and find Waldo among 4 characters. So if you've never seen these, this was a popular series of books, at least when I was younger, where you would have these huge pictures, like on a big colorful page of a book, with all these different characters. And a lot of them have very similar colors to each other. So you can see, for example, the latter 3 here, if you had tiny images scattered all over a page, it would not be very easy to tell the difference because they all kind of blend in with each other. And the goal was to find Waldo. So Waldo is the 4th one here, the one at the very end. And our goal with this Grover search is to find Waldo, essentially, right? So this is an unstructured search problem because we know what we're looking for, but we don't know where it is. Now, an open question, how many qubits do you think we need to represent these 4 characters? I haven't explicitly said the answer to this, but you can probably think about it and figure out the correct answer. Somebody says in the chat 2, that is exactly correct. So if we use 2 qubits, we can label 4 states like this, right? So in general, for Grover search, if you're searching through a list of n elements, or I guess I should say, if you have a list of 2 to the n elements, you're going to need n qubits. Okay, so here we have 4 things, which is 2 to the 2. And so we're going to need only 2 qubits to mark all these possible states. Now, it turns out for Grover search over 2 qubits, we only need to go through these steps 1, 2, 3 once. With more qubits, so again, if you had more elements, if you had 8 elements, for example, you would need 3 qubits. And for that, you would need to repeat step 2 again. So you would do step 1, and then you'd do step 2 and repeat step 2 again, and then do step 3, right? And if you had a larger and larger database, you would need to keep repeating step 2 over and over again. And we won't exactly go into detail on this, but just so you know, here we're doing the 2 qubit example. That's what we're going to walk through. You only need 1 iteration of step 2. Just know that if you go to a bigger list, you would need more iterations of that step 2. Okay, so let's go through each individual step. As I said, steps 1 and 3, pretty straightforward. Step 2 is going to take me a while to talk about. So in step 1, we are going to apply an H gate to both qubits. So we have our two qubits, Q0 and Q1. We're going to put an H gate on both of them. And as I said before, that is going to turn our Ket00 state that we started off with into a uniform superposition over all possible states. So one way to think about this is we're kind of starting off with a 25% chance of our target element being in any of these states, right? At the beginning, we don't know where Waldo is, and so our quantum state should represent that. And it represents that by having a uniform superposition over all possible locations for Waldo, right? We don't know if Waldo is in 0, 0, 0, 1, 1, 0, or 1, 1, and so our superposition is uniform across all of those. Okay, now let's do a little bit of practice. This is nothing new, or it shouldn't be anything new, just applying some principles that we have seen before. The question is the following. Write the state vector for the state Q1, Q0, trying to stick to right indexing here, after an H gate is applied to both qubits, and the hint here is to use tensor products. Okay, so we start off with the state Q1, Q0. Well, I guess I should start off with the state 0, 0, sorry. That is how we initialize. Now, remember that this sort of, when you put multiple things inside a ket like this, that is really just short form for a tensor product, like we learned a few weeks ago. Now, I'm going to apply an H gate to both qubits. And so formally, that would look like this, right? We know that an H gate applied to ket 0 turns into this. Okay, and if you want to verify that, you can just do the matrix multiplication with the matrix for an H gate and the matrix for ket 0, or the vector, I should say, for ket 0. And then we do tensor 1 over root 2, same deal here. They're both zeros, so they both turn into the same thing. Okay, and now we can just distribute across this. So the tensor product, just like a normal product, distributes across addition. And so we will end up with, I'll just take all of my root 2's, 1 over root 2's out front. So it's a big 1 over 2. And then we just multiply. So we have a ket 0, tensor ket 0, plus ket 0, tensor ket 1, plus ket 1, tensor ket 0, plus ket 1, tensor ket 1. And then we use this shorthand notation in reverse to get our final answer, which is what I wrote on the previous slide. As I said, uniform superposition over all possible states. So hopefully doing this kind of math is somewhat review, but if not, we do have some lectures from a few weeks ago that went over how this is done. Okay, so after step 1, we have applied our H gates, and our state vector is now this thing, right? So that's essentially what I had before. If you wrote this as a state vector, you would get 1 over 2 with 1s in all of the entries. And remember, the way that we label these is just by increasing binary order, right? So the top one is 0, 0, then 0, 1, then 1, 0, then 1, 1. And as I mentioned before, this equal or uniform superposition means that we don't know which of the 4 characters Waldo is yet. This is just sort of setting the stage for part 2, or step 2. Now, at the end of step 2, we would like our state vector to be 1, where Waldo is, and 0 everywhere else, right? We want to be able to find where he is. That's the whole point of search. This process is called amplitude amplification. Now, why is it called that? Well, in quantum mechanics, the coefficients on our state vectors are called probability amplitudes, as you might remember, and so that's where the amplitude comes from. Amplification means that we are amplifying or growing the probability amplitude of the state we want, which in this case is Waldo, and at the same time, shrinking the other states, right? So if we amplify that state enough, there will be a very high chance that when we measure, we get the state we're looking for. So just to be a little bit more concrete, if Waldo is in the 4th position, right, like in that picture we had, we would like our quantum state to be this at the end of the algorithm. So 0 everywhere with a 1 where Waldo is. And then when we measure this, we'll get 1, 1 as our answer. And that will let us know that Waldo must have been in that 4th slot. This is where the oracle comes in. The oracle is going to help us do this step. So as I sort of mentioned before, the oracle is just a fancy gate that does a function, right? And so to figure out what this oracle should do, well, we need to think about that a little bit, right? To rephrase the question, we have an even superposition of all states. We want to get to the one state where Waldo is. What could our oracle do to help us? Unfortunately, this is not entirely clear, right? Because I think the most obvious answer to this question, if you just think about it, is, well, we want the oracle to be a gate that goes from 1/2, 0, 0, plus 0, 1, plus 1, 0, plus 1, 1. We want it to transform this into ket 1, 1. Easy enough, right? And in fact, don't we just always want a gate that gives us ket 1, 1 because that's the answer we were looking for? Couldn't we just have an oracle that takes any input and spits out the answer that we're going for? No, we can't, right? Can anybody think of why such an oracle would not work? Do we need 4 different oracles to find each one? Yes, absolutely. So depending on where Waldo is, you would need 4 different oracles. Here we're looking at Waldo being in the 4th position. As somebody says here, it isn't reversible. Exactly. There's a few people DMing me as well. So the problem with an oracle that just spits out the answer like this is that it's not reversible, right? If every input you feed in gives you ket 1, 1, then you're going to have no idea which input you are given if you're only told that the output is ket 1, 1. Therefore, this would be irreversible. So what else can we do, right? What else could we have an oracle do that helps us? Somehow we want it to mark the state that we're looking for, but it can't just, turn our state into it because then it's irreversible. It somehow has to, the way that I like to think about this, it somehow has to maintain the structure of our input so that it stays reversible while marking the target in some way that we can later extract. So think about this for a moment. There are, again, just like Deutsch-Joseph, many possible ways of doing this, but we need some way of keeping this structure, but just marking the element we're looking for in some particular way. Hopefully I'm making this kind of make sense. Somebody says using the coefficient, that is exactly the right idea. And so if I go to the next slide here, you probably already heard the answer in lecture, but hopefully this helps motivate it a little bit. What we're going to do is we're going to flip the sign on the target element, right? So if we started off with this uniform superposition, note that all of the coefficients were positive. We are going to transform that into the same thing, the same probability amplitudes, but we'll flip the sign on the one we care about, which in this case is going to be Waldo. Now, just to kind of point this out, this business of turning a probability amplitude negative is something that you can only really do in quantum computing, right? This is, negative probabilities in quotations. I know it's a probability amplitude, but negative probabilities, that's something that is particular to quantum computing. This is effectively relative phase, and relative phase is something that only exists on qubits, doesn't exist on bits. And this is why, well, this is part of where the power of this algorithm comes from, is that we can use this relative phase to sort of mark the element we care about without destroying the rest of the state, right? So this is the idea of what we want the oracle to do. Now let's think about what gate that would actually be, right? Can you think of a gate that changes the sign of one state while leaving the other states unchanged? I'm not sure if we have actually directly talked about this gate before, but you should have enough knowledge at this point to figure it out if you think carefully about this. So again, what we want is something that leaves most states the same, right? So ket 0, 0 should map to ket 0, 0. Ket 0, 1 should map to ket 0, 1. Ket 1, 0 should map to ket 1, 0. But ket 1, 1 should map to minus ket 1, 1, right? We want to flip that probability amplitude. There we go. Yes. So people are saying controlled Z gate in the chat. That is correct. I will note here, you would have to use a slightly different gate to select a element other than the fourth, right? This is going to work particularly because Waldo is in the fourth spot, but it's pretty easy to extend this to the first, second, or third spots as well. So this is the matrix for the control Z gate. So you can see the Z gate is in the lower right here. And in the top left, we have what happens if the control bit is 0. So just nothing. That's the identity. And again here, this flipping of a phase, or applying any phase for that matter, is something that is uniquely quantum mechanical. Okay, so we answered that question. This is a controlled Z gate. And so our oracle in this particular algorithm is just going to be a control Z gate. Okay, so that took a little while to talk about. Let's now go ahead and apply this mathematically. So the question here, and I'll pop up a Zoom poll for this, is what is the result of applying the oracle matrix on the state vector at the end of step 1? So I'll throw up the Zoom poll and then I will just write some notes as things to remember. The state vector at the end of step 1 was a uniform superposition over all states. So that was just 1 over 2 ket 0, 0 plus ket 0, 1 plus ket 1, 0 plus ket 1, 1. Right? And then the question here is what happens when you apply the oracle, this matrix, to that state? So probably what you're going to have to do is translate this into a state vector and then do matrix vector multiplication, which is something from quite a while ago. So hopefully this is a good review for you to remember how to do that. I'll give you some time to work this out, and then I'll work through the solution myself. Okay, so it looks like about half of you have answered. So I'm going to start writing out this problem because to do it, I guess the long way, doing matrix vector multiplication is going to take a little while, but I'll try to go through this faster. So the matrix we have is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, minus 1. Oops. And we want to multiply that by 1 over 2, 1, 1, 1, 1. That's the state vector we get from this particular state. Okay, so I'll bring the constant 1 over 2 out here, and then we'll start multiplying. So if I do the first row by this column, we should just get 1. Second row by this column, we should get 1. Third row by this column, we should get 1. But now the fourth row by this column gives us minus 1. Just like this. Okay, and then if you write this out as using bracket notation, you should get ket 0, 0 plus ket 0, 1 plus ket 1, 0 minus ket 1, 1. And so I suppose you could have guessed this just based on how we described the oracle working, but what it has done is flip the sign on our target here. Okay, so that is all I wanted to say on that, I think. So we went, I guess I should have solved it on this side, had a bit more room, but that's okay. This is pretty much it. We have succeeded in applying our oracle, right? So what we've done here is we have made the state of Waldo different. We flipped the sign to mark it, but crucially, we also kept sort of the structure of the rest of the state intact. So now that Waldo sort of stands out in some sense, we are in a position to find him. So again, just to remind you what we have now, this is a graphical representation of the probability amplitudes. So I guess if I label this, we have half and minus half. This is the bracket state that we drew out before, and we have a minus sign on the ket 1, 1. So once we have applied the oracle, it is now time to do the diffusion operator. So the oracle has effectively marked the state that we want, right? And we have this state vector now where Waldo is a -1, everything else is a +1. Now, to figure out what the diffusion operator should do sort of intuitively, we again want to think from the perspective of where are we now and where do we want to be, right? And where we want to be, if you remember from before, is still the same. We want to know that Waldo was in the 4th slot. So we want to end up in that state. Now, is there any way we can make this transformation, right? Effectively, what we want to do is we want something that will take a uniform superposition where one of the elements is negative and give us the basis element for that negative slot, right? So here, the 4th slot is negative. We want it to give us the 4th basis element. So how can we do that? How can we develop a gate that has this effect? This is a hard question, so I'm not going to expect you to come up with the combination of gates that does that. Instead, we'll do this in 2 steps. We'll first think about what the matrix should look like, and then we'll decompose that into gates. So in my opinion, the easiest way to think about the way that this matrix should look is to think about what happens for each possible state that has a negative sign in it, right? So we know that this state should become cat11, but we're also going to have potentially, if Waldo was in the 1st, 2nd, or 3rd slot, we also want operations like this to work. So suppose the first one was negative, we would want to turn that into cat00. If the second one was negative, we would want to turn that into cat01, and so on, right? So we basically want any of these states that has a single minus sign to turn into a computational basis state. Again, it's not obvious how to do that from the perspective of quantum gates, but you should be able to think a little bit about it from the perspective of a matrix. Now, the next slide is just going to have the answer on it, but I'll talk a little bit through how you might have come up with it. This is the diffusion operator we're going to use, and you'll notice this looks pretty complicated. We don't really have any single gate that does this. But the general idea is that for each row in this matrix, we can label the rows as cat00, cat01, cat10, cat11. And another way to think of a matrix is that each row indicates the input that will give you that output, right? So again, the 4th row here is the one that we care about for Waldo. If you start with this input, this matrix is going to spit out that output. This is more of a linear algebra thing. And so if you don't have the intuition for this, like no worries at all. We didn't talk about matrices enough to fully understand why this works. But for now, I'll just give you that sort of intuition that when you're constructing a matrix, one way you can think about it is by picking 4 transformations and sort of putting those transformations as the rows of your matrix. That will give you the operation you want. Now, you can go ahead and verify this yourself if you'd like for any location of the minus sign. I am just going to do it for the Waldo version, where the minus sign is down here in the 4th slot. So let's go ahead and do a little bit more matrix multiplication. This one will be a little bit more difficult to work through, but hopefully not too bad. So I'll bring all of my coefficients out front. That's going to be a 1/4. And then we're going to get a vector out of this. And we'll start off with the 1st row. So the 1st row, we are going to get -1 times +1. That's -1, +1, +1, because both those are 1s. And then the last one here is going to give us a -1 again. So if you tally all that up in your head, it's 2 +1s, 2 -1s, and so that goes to 0. You could do the same thing for the other rows. You'll see that one of the -1s, or you'll see that the -1 here creates one -1. The -1 here creates a second one. And then that cancels out the 2 +1s. And so we keep getting 0s. Until the final element, because here we have 1, 1, 1, and 1 again, right? Because the minuses only in this row cancel out. And so here we have 4, because you sum up 4 1s. And then if we work out that multiplication, you get 0, 0, 0, 1. as required. And like I said, you can go ahead and try this by putting the minus sign on any other of these ones, and you should see that it gives you the correct state vector where it sort of marks which element had the minus sign in your original state. So that's the effect it has. How do you do this with gates? That answer is unfortunately quite complicated, right? So we came up with a matrix. There is some way to think about this for sure. But for right now, I am just going to give you the answer. Take this for granted. You can, of course, check for yourself that this particular set of gates creates the matrix that we just saw. It does. But exactly why and the intuition behind it is honestly pretty hard. I think, well, there's an extra resource at the end of the slides today that link to the Qiskit textbook. As usual, it's a great resource if you want to go deeper on these things. And I believe I saw in the Qiskit textbook, they do talk a little bit about the intuition for these gates. But for right now, I'll just say that this is the circuit that does the matrix we saw, and we'll just take that for granted. So with that, we are done step 2. That was quite a bit of time for one step in this algorithm, but the oracle and the diffusion operator are both kind of non-obvious, right? We had to really think about what the oracle should do, given that it has to be reversible and we want it to mark the state that we want somehow. And then the diffusion operator, we had to think about how we went from the state we were in with this one negative sign to the state we wanted, where we had all zeros with a 1 where Waldo is. And both of those took quite a bit of effort. Luckily for us, that effort is going to pay off because in step 3, we just need to measure. And the translation from the measurement we get to the answer to our search problem is fairly straightforward. So that's what the question here is posing. If Waldo is found successfully, what should the final state be? Well, it's just going to be the appropriate label. So in this case, we had our 4 characters, 1, 2, 3, and 4. They were labeled as 0, 0, 0, 1, 1, 0, and 1, 1. And so if we find Waldo successfully in state number 4, we should get 1, 1 as our measurement. And that's it. So step 3 is really straightforward. You measure, and then whatever the value of your measurement is, that tells you where the thing you are looking for is located in the list. Putting it all together, this is what the full circuit looks like. It can look a little bit intimidating, but just to sort of walk through it step by step, we've seen all these steps before. First up here, we have the H-gate step. So this is where we go from ket 0 to our uniform superposition. Then we apply our oracle. So in this case, the oracle is just a control Z gate, but of course you could change the oracle to mark the first, second, or third states as well. And this is going to keep us in a uniform superposition, but the only difference is it will flip the phase on our target element. Once we have that special superposition with the 1 negative sign, then we do the Grover diffusion operator, which is that funky matrix that we found, which translates to this set of gates. And that is going to tell us which element in our state vector had the minus sign. And so in this case, we expect that this will give us the 1, 1, 1, 1 element that had the minus sign. And then step 3 is to measure right here at the end. So big, complicated looking circuit, but at the end of the day, this is just the 3 steps that we talked about. Okay, so the only stuff I have remaining is to go over this in the IBM Quantum experience. We do have only 5 minutes left, so I will probably go over time. But I think that I want to try answering some questions just to make sure that everything we've talked about so far is clear. Because honestly, I think that if you're comfortable with Qiskit, you should be able to go from this picture to Qiskit code and executing it on the simulator. That's all we're doing in the notebook. So I'm going to pause now and take questions, because I know I've been kind of ignoring questions. I wanted to make sure I got at least this far by like the end of our time. So now we can talk a little bit more. Okay, so if anybody has unanswered questions or questions they would like me to answer again, feel free to just copy paste them. Otherwise, I'm just going to quickly scan the answers that other students have given and confirm that this all looks good. So somebody asks, I have one doubt that if we can mark the character with the help of the oracle, then why are we doing the other steps? Yeah, good question. So the oracle, okay, I think the easiest way to think about this is in two pieces. Number one is if you accept that the oracle we have now, where it sort of adds on this minus sign, if you accept that that is the oracle we must use, then stopping here is not going to work, because the state we have here is 0, 0, plus 0, 1, plus 1, 0, minus 1, 1. And if you measure this, you're just going to get 0, 0, 0, 1, 1, 0, or 1, 1 with 50%, or sorry, with 25% probability, right? Just because this has a minus sign doesn't mean it's going to be observed more often or anything. So if you stopped here, there's no way of knowing what the oracle has told you, right? The information the oracle gave you is kind of lost to your measurement. Instead, we have to do this diffusion operator to effectively translate that information from the oracle into something we can measure. And that's why we need to keep doing that part of the algorithm. Now, let's take a step back, though. Why do we need to use this particular oracle? Why can't we use an oracle that directly gives us the answer as something we can measure? Well, that is the thing that I talked about before, where it would be irreversible. If the oracle did something that directly gave us the answer, it would lose too much information about the original state to still be reversible. And so the nice part about this oracle is that it keeps the form of the original superposition. So even if I had different coefficients, right? Maybe I had like, I don't know, root 3/8. And here I had a root 1/8, something like this, like some weird coefficients. All of those stay the same. The only difference is the minus sign in front of the ket 1, 1 state. And so that effectively makes this gate reversible. Hopefully that makes some sense. And then some people in the chat gave justifications based on superposition and interference, also totally valid. And that's effectively what I just said. I just didn't use those words. Okay, so somebody asked, let's say we have to run this for something really complicated. How do we know if it's the right answer at the end of the measurement? Usually when you're doing a search problem like this, it falls into a category of problems. This is going to dive just a little bit into computer science. That is my background, so we can talk a little bit about it. Usually the problems that you solve with this are problems that are called NP. And you might have heard of these things, P and NP. They generally refer to classes of problems that are sort of difficult or easy to solve, very generally speaking. What NP really means, though, is problems that are easy to check, but hard to solve. And that's usually what we're going to be dealing with when we use Grover's search algorithm. So we're assuming that if I give you the answer, you can fairly easily verify that it is correct. But if I told you to just find the answer on your own, you would have a lot of trouble doing so. So a very classic example of this is prime factorization, right? If I tell you that 337, I don't know if this is a real example, by the way, this could be completely wrong. Suppose these are both primes, and I tell you that these two things are equal to some other big number, right? I don't know, I'm just making stuff up. This is not supposed to be correct, right? Suppose I tell you this, right? And I tell you, hey, these are the two prime factors that multiply together to get this number. You can fairly easily check that. You just go to your calculator, plug this stuff in. If it works, then I was right. But if I just give you that number on the right, and I tell you, hey, what two prime factors multiply together to get that number? Turns out this is really hard. And pretty much the best ways to solve this come down to some variation on just check all the possibilities, right? Start off with, okay, can I multiply 2 by something? No. Okay, can I multiply 3 by something? Oops, I should have done 3 by something. No. And so basically what you're doing is you're going through every possibility and checking the answers, right? Because again, this problem is easy to check, but when I say hard to solve, it's because there's so many possible answers that you would have to check. It would take you forever. And that's where Grover search is handy, right? It will allow you to search for the answer you're looking for without explicitly checking every single element. This, by the way, prime factorization can be thought of as a search problem as well, where your list is all of the possible primes going up to this number. And what you're trying to check is which of those primes actually multiply together to get the number you're looking for. Okay, so somebody asks, in this example, we are looking for the fourth element. How would you define the matrix if it's the second or third one? So if you wanted to do an oracle for, say, the third position, right? The way that you would do this, I would recommend, is using X gates to change your initial state. So let me demonstrate. If we wanted to search for the third element, or if we wanted our oracle to sort of mark the third element, what we would want is something that does the following. You would want all of these to translate to ket 0, 0 stays the same, ket 0, 1, but then we get a minus ket 1, 0, ket 1, 1. Okay, so what I'm going to do here is I'm first going to apply a control Z gate, just like before, right? So no matter what element you're looking for, your oracle is always going to involve a control Z gate. But now, in order to get to the state that I want, I need to somehow turn this state with the minus sign into the third state, right? And the most clear way to do that is to just flip the second qubit, right? Flip the second qubit. So we're going to do an X on Q1. So assuming we have Q0, Q1. Or I guess, bright indexing is messing me up again. Let's just say the second qubit on second qubit. Okay, so that's going to bring this up here. It will bring this state down here, right? Because we flip 1, 0 should now become 1, 1. And then it's going to exchange these two as well. And that will get us the oracle we want. So hopefully that makes sense. You can essentially use these X gates to move that minus sign to whatever state you want. Right, so there were a couple of questions about that. This week is quite complicated. I agree. Grover search is a hard algorithm to understand. I think like Grover search and Shor's algorithm are the two that take quite a while to wrap your head around. Although I hope that some of the ideas from Deutsch-Josa were at least somewhat helpful in understanding Grover. Okay, so somebody asks if the oracle is based on the item you want to find, so in this case, the 1, 1 position, will it still find it and make its probability amplitude negative? I think, so maybe as an example, there's a really sort of popular example of how the oracle in this case can be generalized, because I'll be the first to admit that the way we've set it up here seems kind of trivial, or well, it's hard, but it seems sort of like a meaningless problem, right? Because in order to design the oracle, you had to know where the element was in the first place, right? And that doesn't seem very useful. So maybe after I do the stuff in IBM Quantum Experience, I can talk briefly about how you might design a more useful oracle for a more useful problem. Yeah, so I'll maybe just put a hold on those questions for now. Yeah, so somebody asked that in a direct message. How do we make this oracle without knowing which state we're looking for? I will answer that. Okay, so actually quite a few people are answering this. Yeah, to those people who are asking who need to leave now, because the required content is not quite done yet, but I know I'm going over time. The only part you're going to miss is me coding this circuit, right? So I'm going to go on to the IBM Quantum Experience and I'll show how you do the Qiskit code for all of this, but that's it. So it should actually be pretty quick before I return to just answering questions. Okay, so you know what? Why don't we do a little bit on oracle design now? Just because I think, in my opinion, writing out the circuit in Qiskit is not the most important thing. I think that most of you will be able to do that. Figuring out how you make useful oracles is a little bit more difficult. So let's talk about that. In the most general version of this problem, when you're going through a search problem, actually, sorry, just to answer one quick question, will the code be for more than 4 numbers? No. So the code is literally just going to be this circuit, like as you see it here. I think there might be some extra stuff like in the extra content in the notebook where they talk about how to build larger circuits, but I'm not going to go over that. Okay, so let's talk about how you could make a useful oracle. In the most general version of this problem, the way I phrased it to you is you have 4 elements and you want to find one of them that matches some description. That is too general to talk about any useful oracles. So in order to do this more properly, we have to think about an example. Now, this example is given in the Qiskit textbook, so you can feel free to refer to that if you'd like. We're going to talk about a game called Sudoku. Right? So some of you might have played this before. It's a game where you sort of have to fill in numbers in a grid. We're going to go to a smaller version of it, though, and we're going to do just a tiny, tiny 2x2 Sudoku. And into this grid, I have to fill 0s and 1s. And the rules are as follows. If I fill a 0 here, I cannot put a 0 in the same row or in the same column, right? And likewise, if I put a 1 here, I cannot put another 1 in the same row or the same column. So pretty straightforward, right? And you could probably already tell what the solutions are to this problem because it's tiny, right? But if we design an oracle for this problem, the oracle should seem a little bit less trivial. So let's say that our states are going to be represented by just lining up whatever bits we have in this grid. So 1, 2, 3, 4. For example, if I had the state 0, 0, 1, 0, that would be represented by ket 0, 0, 1, 0. Right? So this is going to be a 4-qubit problem. If I had a state like 1, 1, 1, 0, that would be the state ket 1, 1, 1, 0. So we're just translating these into qubits just so we can actually use these in the quantum algorithm. Okay, so what the oracle now has to tell us is the states we're looking for. And the states we're looking for, we don't necessarily know what they are, right? I know we do in this case because this problem is relatively small. We don't necessarily know in general what they are, but we know what constraints they satisfy, right? In particular, the oracle knows that the state we're looking for should have different values in every row, right? So it'll look at these 2 values, for example, and it'll know this is not what we're looking for immediately, right? But if it saw a state like this, it would know that this is the kind of state we're looking for because each row and each column have different values. So that's something you can build into an oracle. If you want the details on this, the Qiskit textbook actually tells you exactly what this oracle would look like as a matrix with gates and stuff. I won't go into that, but I guess the general point I'm trying to make here is that you can design an oracle that enforces certain constraints. The constraint here is that you need different values in each row and column. Knowing the constraints is not the same as knowing the solution to the problem, though, right? In this case, it just so happens that we can look at it and solve it fairly easily, but you could easily come up with a problem that has simple constraints, but is very difficult to find the answer to, right? For example, that traveling salesman problem I said, the constraint here is just that the salesman has to travel between all the cities. That's easy to state, but if you had like 50 different cities, there are so many different paths you would have to try that it becomes computationally infeasible. And that's the kind of thing where Grover search can be handy. Okay, I don't know if that helped. Once we get into the stuff that I haven't prepared, I'm not always as coherent as I like to be, but maybe this gives some idea. And again, if you do want more details, I would highly recommend the Qiskit textbook page on this, which is linked in the, if I just skip to the end here real quick, it's linked here in the further reading. Okay, So let's hop over to IBM Quantum Experience. I don't want to hold off on this too long, but I did think it was important to answer a few questions. So I'm going to go ahead and share my screen. Here we go. Okay. So this is the Lab 21 Python notebook. It's on Grover's algorithm. If we go to the overview here, we have three main sections. The introduction, I'm honestly just going to skip because we have already talked about Grover search in much more detail than that. Then we will go through and implement this. Each of the three steps, we'll see how to simulate it. And I might just skip the experiment on real devices for now. I mean, it's a fairly straightforward extension. Okay, so the introduction, we talked about that. So let's go ahead and implement this. We will first start off with the necessary imports. So here we have everything that we usually have. This least busy thing might look new. You'll see how that's used at the very end of the notebook, but it's a fairly straightforward idea. So we'll run this to get everything fired up. And as soon as the star turns into a number, there we go. We are good to go. As a quick refresher, the three steps that we're implementing is to apply H on both qubits, apply the oracle and Grover's diffusion operator, and then measure both qubits. And just copy pasted from the slide, this is the circuit we want to create. Okay. So just like before, when we've done these notebooks with algorithms, we're going to split things into functions. So we're going to have a function for step one to start things off, and that is applying the H gates. We're going to call this function initialize. You can call it whatever you want. You could call it step one if you wanted to. And as always, it's going to take our quantum circuit as an input. Now, all this step is going to do, we're going to assume that we have a 2-qubit system here. So we need to do qc.h for the Hadamard gate on qubit 0, and then qc.h on the second qubit, qubit 1. Okay, so again, just using that circuit name .gate name notation to fill in this circuit. So let's run this to check that we have everything correct. So we're going to go ahead and create a 2-qubit quantum circuit, which remember is done with the quantum circuit keyword. And then you pass in the number of qubits. So this is a 2-qubit quantum circuit. Then we're going to call the initialize function. So I just do initialize, if I can spell correctly, Grover circuit, we've called it here. And then we're going to draw it. So, oops, I forgot to run this cell. So we'll want to give us that function definition. And then I will run this to draw the circuit so far. Quantum circuit is not defined. Oh, I see. Okay, so when you use this version of Qiskit import, you have to do q.quantum circuit. That's my bad. So I'll fix that and hit run. There we go. Okay, so this is what we're expecting, right? If I just go up and compare to our target circuit real quick, you can see that we've built up to this first barrier. All right, step 2 is the big one, applying the oracle and Grover's diffusion operator. So the oracle that we want to apply is this thing. And remember that that is just the control Z gate, right? Excuse me. Okay, so to do the oracle, it's pretty straightforward. We just have to do a control Z. And if you remember, the way that we did a control X gate before was CX. And so the way we do a control Z is going to be CZ. And we're going to control, we're going to control on the target qubit, or I'm sorry, control on the 0 qubit and target qubit number 1. Now we're calling this oracle 1-1, by the way, just to indicate that this is going to sort of mark or pick out the 1-1 element. You could likewise define oracles for the 0-0, 1-0, or 0-1 elements using X gates, like I talked about before. So that's pretty straightforward. We will do that and run it. And then again, we want to call the oracle 1-1 function. So I will do oracle 1-1 on our Grover circuit. Right, so this is going to go ahead and stack that control Z gate and then another barrier onto our circuit. And now we'll draw it again to see what this looks like. There we go. So again, we're building up to that full circuit that we saw a picture of. And finally, we have the diffusion operator, which was kind of this magical thing that we found first using matrices. And then I tossed this combination of gates at you and said, trust me, this works, which you can totally verify if you want to do the matrix multiplication here. It could be some good practice. We're going to call this function UG. I'm not exactly sure why it's called that, to be honest, but we'll call it that and roll with it just to match what you have as well. This is going to be a little bit longer because we have, what, 1, 2, 3, 4, 5, 6, 7 gates to apply. So let's just get started. Circuit name, dot gate name. We're going to start off with our H gates. Okay. Now we have 2 Z gates. So same idea, but now it's going to be QC.Z on both qubits. Then we're going to do our control Z gate. So remember that is a CZ. 0, 1. And then to finish things off, we have our 2 final H gates. And then we'll do a barrier just to mark where this ends. So just to recap, this UG thing should do our diffusion operator for us, which was the matrix that hopefully you have some intuition for. The gates, maybe not so much, but you can just confirm that these gates do the matrix that I gave you in the slides. I'll go ahead and run that. And here, again, we'll call the UG function on our Grover circuit to tack on that extra bit. And then I'll run this. And there we go, we're in business. So we have our initialization, we have our oracle, we have our diffusion operator, and now the only thing left is step 3, which is going to be measurement. Now, usually we used circuit name.measure. There is a shorthand if you just want to measure all your qubits, you can do measure all. And so that's what we'll use here. And you should see that if I now draw the circuit, indeed, it has added some measurements for us. So this is just a shorthand for Grover circuit dot measure. And then remember, you tell it the quantum bit that you're going to measure and the classical bit that you want to store the measurement on. So here we would measure qubit 0, store it on classical bit 0, and then we do another measurement, circuit.measure, qubit 1 into classical bit 1. Right? And so this kind of pattern of measuring qubit I for any I and storing it on classical bit I is so common that they have just a shorthand for it. You can just do measure all. And that's it. So this is our full Grover circuit. Hopefully, as you see, fairly straightforward to doing code. We're just using H gates, control Z gates, and Z gates. The theory behind it is what is really quite a bit more complicated in this case. And that's what we went over in the slides. So the final little bit I'll do is just to simulate it and confirm that this works. As usual, we'll use air.getBackend to get the QASM simulator. We'll use execute 1,024 times so we get some nice results. And then we will plot a histogram of this. So I'll go ahead and run that. And as expected, we get 1, 1, which points to the 4th position 100% of the time. So here, the QASM simulator does not simulate error. So if you go ahead and run this on a real quantum computer, you probably won't get 100% success, but you should certainly get the majority of your measurements falling in this 1, 1 category. Okay, so I think I will leave out this section 2.5 here. Feel free to use it yourself, but this is just going to run things on an actual quantum computer. Okay, so for the time being, let's hop back to the slides. We are just about at the end of the required content here. There we go. So to finish things off, I'm just going to go over some key takeaways, and then I'll point you to the further resources. I should have probably done the post-lab Zoom feedback a little bit earlier. That was my mistake, but we will do it just for good measure. So key takeaways. The sort of main headline of Grover Search is that it allows you to search an unstructured list in root n time, right? Which is a quadratic speed up over the classical version, which is to just check every element. And that, of course, is order n time. So the Grover's algorithm has 3 steps. You first put all the qubits in a superposition by applying H gates. Then you do the oracle. So the oracle is going to mark your correct state. The diffusion operator is then going to translate the mark into something we can measure. And then step 3 is to measure. Pretty straightforward. Okay, the final point here is just sort of a high level, I guess, picture of exactly what this is doing, right? So we talked about these 2 things, superposition and interference. Those are both utilized in Grover search, just like they are in Deutsch-Josa. And we take advantage in Grover search of this unique property where we can manipulate the sign of the phase on particular qubits. That's something you cannot do classically, and it's part of what gives us this quantum speed up. Further reading, like I mentioned before, there's a bunch of great resources here. The Qisk textbook I would especially recommend as a good resource for learning more about how Grover's algorithm works. They have a 2-qubit example, but I think they also have a 3-qubit example and a n-qubit example. So that is a great one to look at if you want to learn more. I will just caution that this algorithm does get more complicated for n qubits. I totally think it's within your realm of understanding. It requires you to think about things differently, though. So if you go to their textbook, they'll talk more about this, but sometimes Grover search is explained in terms of reflections, and you can kind of look at these graphs, and there's nice visuals for how it works. Not required for the 2-qubit case, but as you start growing to more and more qubits, you kind of have to start thinking about it in this more graphical way. Okay, so post-lab Zoom feedback. I apologize for not doing this earlier, but we will go ahead and see how people are feeling about Grover search. I guess one last thing I'll mention on this is, much like last week, I hope that as much as this lab has hopefully helped you understand things more, I hope it also tells you, what level of understanding we expect, right? So for example, we don't expect you to be able to derive the diffusion operator or explain how you come up with it or come up with your own version of it. No, like you just need to understand what it is, roughly what it does, which is sort of this translating from a mark that the oracle creates to something we can measure. But we wouldn't expect you to come up with that, right? Like as you saw, the circuit for it was really complicated. I kind of waved my hands a bit with the matrix derivation, but generally speaking, not required. All we want you to understand is these high-level concepts of how Grover search uses superposition and interference to achieve a quantum speedup. Okay, so I guess that brings us to the end. Oh, I totally forgot I have optional content. Right, on oracles. Okay. So I think because the optional content, I think, is a little bit detached from most of the questions that are being asked right now. And so I think I'll do the optional content right at the end of the lab, just because then if you wanted to leave before that, you can. For right now, I think I'll answer more questions, though, if that's okay with everyone here. I guess just to clarify, this is the end of the required content. Technically, I ended it a while ago at the end of the slides, but the IBM quantum experience stuff was technically part of it. Now we're done that, though. So if you were only here for the required content, I apologize for taking longer, but we are officially done at this point. Okay, I'm going to take a quick drink, and then we'll go back to questions. All righty. So somebody direct messaged me. So somebody asks about the traveling salesman problem and other optimization problems. Could you elaborate on how the oracle fits in, since it's essentially a checker of some form? Yes, this is a great question. So, the first thing I'll say is that there's a couple different ways of implementing optimization schemes in like a Grover search framework. I'll talk about one of them here, which I think is the easiest to understand. So most optimization problems, including traveling salesman, so let's take that as an example, it's often abbreviated as TSP, traveling salesman problem. And again, just to sort of outline exactly what this is, I'm not going to go into tons of detail, but suppose you have a map of a whole bunch of different cities. I don't know, I'll make it look a little bit more random. So suppose you have all these different cities and you know the distances between them, right? So obviously this city over here is way further. You need to find a way for a salesperson to travel between all these cities and hit every single city by traveling the least distance possible, right? So there's some paths that are obviously inefficient, right? So if I started in this state over here, I probably don't want to go all the way out here before coming back here, right? In this case, it would have made more sense to just go like this. It'd be a shorter distance, right? And so on little small examples like this, it's easy, but if you start to have more and more cities, this becomes a lot harder. Now, this problem can be broken down into sort of two parts. The first part is constraints. So constraints are properties that have to be true of the solution, right? And in this case, the most obvious constraint is that the salesperson has to visit every city, okay? So that's I guess, the only constraint here. Have to visit every city. Okay. And the second piece is what we'll call an optimization. The optimization is to find the shortest distance, right? So another way of phrasing this is among all possible paths that meet the constraints, which has the shortest distance. Okay, so hopefully that breakdown makes sense. It's often nice to try and break down a big question like the traveling salesman problem into smaller chunks, right? So now we have the constraints to think about, and we also have the optimization to think about. So one way you can implement this using Grover Search is to implement the constraint using your oracle. So your oracle is going to take some quantum state representing a path. So I won't talk about how we do this, but suppose you have some state that does this path, right? The oracle is going to reject this, right? And the oracle will have some way of knowing whether your solution meets these constraints. And so then what your Grover search is doing is effectively picking out all of the possible solutions that you can then optimize over, right? So what you then do is you add a second piece to your oracle. You say the oracle should check for constraints, and it should also check whether the path is less than a certain distance. So a simple sort of yes/no question, right? So suppose I want my oracle to tell me, does it violate the constraints? If not, is the path shorter than 100 kilometers, right? Something like this. And so your oracle in this case might actually come up with several different answers, right? There might be several paths that meet the constraints and are less than 100 kilometers. And that might be good enough for you, right? You might not care about the true optimal path. You might just care about getting a path that's good enough. But if you wanted to get the optimal path, you could just start decreasing this number, right? If you see that there's a whole bunch of solutions for 100 kilometers, see if you can find one that's less than 50. And if there's still a lot of solutions, see if you can find one that's less than 25, and so on, right? So you keep decrementing this number until you end up with only one or two solutions, and that's how you know you have your optimal solution. I know this is not very specific, but that's kind of the general idea, is you break things into constraints and optimizations, and then you design an oracle that sort of gauges both of them. Okay, let's see. So somebody asks about doing an oracle for one of the first three positions instead of the fourth. I did give an example of that earlier, so I think I won't review that again. Okay, so somebody asks, what if we flip every position except for the answer and get it to interfere with a copy of an equal superposition state? Wouldn't it directly give us the answer as every other block gets destructively interfered? Why is it not possible? So good question. I think roughly what you're saying is the oracle would do the following. it would bring us from our initial superposition. And now your different proposed oracle would mark everything else with a -1, right? And then you're saying we would somehow interfere this with our initial superposition state. And I think the idea here is you're saying that the first, second, and third would cancel out because it's a 1 and a -1. I think this general idea works. The devil would be in the details, though, right? How do you actually do this with quantum gates? Because honestly, this is pretty much the idea of Grover search, right? Is you sort of mark something with a negative phase, and then the reason we needed that big complicated diffusion operator, sorry, was to turn these phases into something we could measure. So this kind of interference step that you're describing here is not super straightforward, right? It would require something like the diffusion operator. Oh, could I remind what the optional content is? Yes, sorry, the optional content is more on oracles. So I'll be talking a bit more about how you develop sort of more practical real world oracles and a bit more on how to think about them. Yeah, okay. So somebody says, sorry if I'm going ahead a bit, but how is traveling salesman different from minimum spanning tree? You are going ahead a little bit, but I guess I will quickly give you an answer now because I think it is a fairly straightforward difference. So these are two different problems: minimum spanning tree, MST, and TSP. Traveling salesman problem is a path that hits all cities, and so you could travel from one and follow this path all the way through, and you're looking for the shortest such path. Spanning tree doesn't have to be a path like this. A spanning tree could look like this, for example. Right? That would be a minimum spanning tree, but not that would be a valid spanning tree, but not a valid path for the salesperson. Right? So it's just a matter, you are looking for the shortest in both cases, but it's a matter of what types of graphs are going to be valid. Okay, so I think, does anybody else have questions about Grover search? I really want to do my best to try and help you all understand what this algorithm is doing. I think it is quite complicated, and so I totally understand if things don't make sense, especially on the first run through. Okay. I hope it's not just the case that everybody who did not understand already left. Everybody who's still here is okay. Hope that's not the case. But anyway, okay, so shall we do the optional content then? We'll talk a little bit about oracles, and then that will wrap up our lab for today. And then I won't see you all for another 2 weeks, unfortunately. But I will say, I think the weeks coming up after spring break, I think we only have like 2 or 3, don't quote me on that, but like 2 or 3 lectures after spring break. Those are going to get really fun because we're going to talk a bit more about physical implementations of quantum computers. I don't know if we'll do any more algorithms, but hopefully it'll sort of bridge the gap between everything we've been learning in theory and a little bit about how it's done in practice. Because I know people often ask questions about how we do these things in practice. Okay, so somebody asks, square root of 4, oh yeah, this is a great question, actually. I should have explained this. So we said that Grover search was big O of root n searches, right? And if you plug in 4 as the number of things that we're searching over, that should indicate that we're doing 2 oracles, right? That we need 2 oracles. But if you think back to the quantum circuit that we wrote in the textbook, or in the notebook, sorry, that only had 1 oracle, right? The control Z gate. So this is a technicality of big O notation, where big O notation absorbs constant factors. So if you have something that's big O of root n, what that really means, and I've kind of glanced over that by saying about in the past, what that really means is the real number is some constant c times root n. And so in our case, the constant c is just half, right? Half times root 4 is 1. So this might seem like a little bit of a cheat, but again, it just comes from the fact that big O is trying to measure the rate of growth. And if this constant factor stays the same, it doesn't affect the rate of growth, even though it would affect the exact answer you get. Oh, cool. Yeah, so somebody says there's 4 lectures and 3 labs left. There you are. All right, let's go ahead and do the optional content, and then I will wrap things up for today. So oracles are something that have come up both last week with Deutsch-Josa and this week with Grover search. And you can ask the question why we introduced this concept at all, right? I've given you some justification here and there about, when we talked about Deutsch-Josa, it was that our original function was not reversible. And so we had to come up with an oracle. In this case, we needed a way to mark our target element without destroying the superposition. And so for that, we needed an oracle, right? Oracles always generally come down to being about reversibility in quantum computing. But when you talk about oracles more generally, they can exist in classical algorithms as well. And the common thread between quantum and classical oracles is that they all allow us to reframe how we think about solving a problem. Now, this is a very subtle point, so I'm not sure if it'll make sense on the first run through, but I'll give it a shot anyway. The regular approach of solving, for example, the search problem is to say, I have a list of n entries. How do I find where the entry I'm looking for is, right? This is kind of the equivalent of going from my equal superposition, right, in the beginning, and going to my answer immediately, cat11, right? That's the regular approach. And we found that sometimes that's not going to be reversible, but more generally, that could just be really hard, right? Like that is pretty much the whole problem of search, right? You want to start with this uniform superposition over all possible locations and end up with the location where your target is. That's the whole problem we're trying to solve. And so rephrasing it as, where do I find my element, doesn't really help anyone. What oracles usually let us do is they let us break up the problem into more pieces, right? So an oracle says, well, suppose I have some magic box that marks the entry I'm looking for. If I have this mark, is there then a way to extract the answer? And in the case of the Grover search algorithm, there was. That was the diffusion operator. But notice how introducing this oracle essentially allowed us to rephrase the problem. Instead of trying to come up with something that does this, we were trying to come up with something that does this. And that turned out to be an easier problem. So more generally, what oracles let us do in both classical computing and quantum computing is they allow us to reframe the problem. They let us break it up into some pieces so that we can solve a problem that's hopefully a little bit easier than the original one we are trying to go for. Now, the only caveat here is, of course, okay, we solved this easier problem. Can we actually come up with an oracle that lets us do that? So in the past couple of labs, we've kind of just said, don't worry too much about how we make the oracle, right? We've told you how to do it in some specific cases, but oftentimes those were a little bit contrived because constructing the oracle required knowledge of the solution to the problem, right? Which doesn't help too much. I guess that's pretty much all it says in this slide. For both Deutsch-Josa and Grover's, we discussed which gates implement the oracle if we already know the state that the oracle marks. But that was kind of like circular reasoning, because if we already knew the state that the oracle was going to mark, then we already knew the solution to our problem. So the question then becomes, how does the oracle sort of know where to place that minus sign? Right? In this case, we knew to place it on the 4th element because effectively we already knew the solution to our problem. This turns out to be a bit of an open question. And I think I even alluded to this last week when people were asking about oracles. Oracle design is really hard. We know that designing algorithms using oracles is an effective way of solving certain types of problems, but it doesn't make it easier overnight, right? Designing the oracle is still going to be hard. One really nice analogy that one of our other TAs, Phil, I don't know if he came up with it or if he just heard it from somewhere, but one really cool analogy is, imagine you're searching for a literal needle in a haystack, right? So this is an expression, but let's imagine this literally. You have a huge pile of hay and you're trying to search for one metal needle, right? The standard question to that would be, find me the thing in that stack that is metal, right? And so you have to go through every piece of hay, check that it's not metal until you find the needle. What an oracle effectively does, though, is it's kind of like a magnet, right? You hold this big oracle on top of your haystack, and it's going to affect the needle that you're looking for differently than everything else in the haystack. Now, in the case of a magnet, it literally pulls the needle for you, and so it sort of answers the question. But more generally, oracles don't have to fully solve the problem. They just have to treat the thing you're looking for a little bit differently, right? So for example, in Grover search, we saw it put a negative sign. It didn't solve our problem directly, but it treated that one element a little bit differently. And that's generally what oracles do. They introduce some kind of differentiation between the thing you're looking for and the things you aren't. And then you use other parts of the algorithm to extract that answer. The last point here is just a note that oracle design for example, optimization problems, right? Like trying to design effective oracles for a traveling salesperson. That is an open area of research, right? There's many possibilities, and we're not really sure which ones work best. And so that's one of the things that I guess I don't really know too much about, but it is an active area of research. Very interesting one. So I guess that's not a maybe super satisfactory answer, but part of the reason is just that we as humanity don't know a super satisfactory answer yet. This is kind of the edge of our knowledge at this point. So take that for what you will. There is a lot more to learn on this, but oracles remain a difficult problem. Cool. Okay, so I think that brings us to the end of the optional content. I think I'll also wrap things up here for the lab. If you do have any other questions, feel free to post them on Piazza. But just a quick reminder, there is homework this week. It is to fill out that course certificate name form, but nothing else to do with the actual content. So hopefully the name form doesn't take you too long and you have some time to enjoy the next 2 weeks off. Have a great break, and we'll see you again in 2 weeks. Bye.